Artificial intelligence is taking the world by storm, from marketing to manufacturing to research. And with it comes a lot of questions. What will the future look like? Is it going to take over my job? It's already more active in our everyday lives than you might think. In the voice assistants in our phones, in targeted advertising, and even in our email inboxes. And while many people think of AI as a robot that looks, acts, and thinks like a human, we're still a long way away from that. Right now, we can think of artificial intelligence as an umbrella term, with machine learning, image classification, and speech recognition as subsets of AI that fall underneath. Algorithms are trained to learn on their own by detecting patterns in a set of training data. They then make predictions and draw conclusions about future outcomes, getting smarter as they see more data. One of the pros of artificial intelligence is the speed at which it's able to make calculations and find solutions, sifting through a huge amount of data. And with AI's capacity to quickly process more data, the demand for more power in a small amount of time is steadily increasing.
AI is a pretty broad idea and it's not easy to define. Basically, anything when the computer pretends to have any kind of idea of what's going on, you could think of AI. So when you tell your phone, talk to Siri, talk to Alexa, this is AI. A component of it is AI. When the car drives by itself, it's AI. When the email inbox sorts your email or so, that's AI. So you may remember a long time ago there was the Microsoft Office assistant. It was this little paper clip going around and telling you all kind of things. This was early attempts on AI. We're kind of like in the, fourth, fifth, sixth wave. And people have tried for a long, long time to let the computer understand what's going on and react to it.
That's Franz Franchetti, a professor of electrical and computer engineering in the College of Engineering at Carnegie Mellon. Franchetti works on the systems that make AI run, special accelerators and hardware that are really the backbone for AI. He works with experts across multiple domains to understand the requirements needed to build optimal hardware systems and make algorithms run more efficiently. So Franz, how do hardware systems need to improve in order to support AI systems and applications?
We have a lot of data sources, and so with big data and deep learning and these new methodologies, a lot of ideas of AI that didn't work so well in the past because they lacked that, nowadays suddenly start to work. So the basic operations tend to be pretty similar. But the one thing that happens is that because a lot of the data is way more approximate than usually, you can get away with simpler data types, basically less precise numbers. And that's driving a lot of the current innovation to make hardware faster. Think about it like that. If you want to simulate flying to the moon, you need pretty good accuracy, otherwise you fly to Mars instead of moon. But if you want to figure out if that's a cat or a dog by looking at the picture, the pixels, there is just not so much information in the pixels as if you have to get a trajectory all the way to the moon. And so because of that, hardware, even though it's solving the same kind of problems, can be optimized in a different way. And so one of the things that's happening is that we use lower precision. So the latest, greatest artificial intelligence accelerators, like in graphics cards, they use much fewer significant digits because we just do not need so many digits to figure out some of these pattern recognition tasks.
So even though hardware is being used to solve similar problems, it needs to be optimized. What are some challenges here?
In AI, the problem you get is that the dependencies or the relationships can be way more random and way more far distance in a sense. And that puts a lot of pressure on the computer systems that have been optimized for what's called locality for the last tens of years, last decades. Basically, the idea is whenever you touch some data, you'll touch close by data because it's somehow related. With a lot of the modern AI approaches, that's no longer true like that, and so hardware suffers from that. And so these are basically the two major changes. The one thing is you don't need so much accuracy, but the other thing is you don't know where you're going to go next. And these two things change the game. If you can have lower accuracy, where do you want to do that? Because it's a very fine line between producing random numbers and producing the right result. And so there is, from fields like numerical analysis and optimization, it's always the question, how much accuracy do you need? And so Accuracy translates into hardware cost, and if you can get away with less, then your hardware can get more efficient, can get smaller, you can put more on the same area on a chip, and so it gets better. The other problem, though, is when you get so completely random, then most of these standard techniques in computer architecture to make computers faster break down, because we've optimized computer systems forever for that locality. It's one of the bedrock principles. And once you give that up, it becomes hard. And so the question that I'm asking in my research is, can we know from the problem something else like locality that we can leverage? Because if you don't know anything, it's totally random and you can't do anything. And so the question is, if you understand what kind of problem you're trying to solve, is there a way to leverage that knowledge and say, okay, we're not in physical space, so we don't have 3 dimensions, but we know that most people have only so many friends, and therefore the fan out going from one to your friend is limited. Or other properties like that. So you have to look deep and carefully at the problems. What kind of properties can you find? And these properties are not always sitting there and kind of like screaming at you, hey, I'm here, use me. It's sometimes really hard to find out what to use and what kind of transformations to do.
Franz, you've talked about looking at the problem you're trying to solve, not just paying attention to the hardware. So how do you get from that problem down to how to implement that in the hardware?
So basically, one way in engineering and computer science to solve really, really complicated and complex problems is to use abstraction. So basically what we do is we put in basically artificial layers of boundaries where we say, whenever you work at a certain layer, you really only care about your upper and lower neighbor and not really farther up. So for example, we break logic gates like and or not, and say then we can build arithmetic units out of that. That would be like adding and multiplying. And then you go a level up and write a computer architecture that then can actually run a program. And the program needs to know how to do adds and multiplies, but really doesn't need to know how the gates underneath implement it. And then farther up, your email system doesn't really need to know how the program is run. And the network doesn't really need to know how the bits are really transmitted over the wire. So there's always this concept of layers, and that's how engineers basically make everything possible. But by the moment you put in these layers, you put artificial boundaries. And if you need to optimize, sometimes these boundaries get in the way. And so what we're doing is we're talking to people up and down these layers, what we call the stack, to see what kind of problems are they trying to solve and what they care about and what they don't care about.
In talking about optimizing, you also talk about choosing between certain things. Will we ever get to a point where we don't have to deal with this? And what changes with AI?
The one constant thing in engineering is you have to deal with trade-offs. You're often faced with the situation you have 3 things you want and you can only have 2, and the third one you have to give up. It's kind of like area, power, and performance, and things like that. So you can build a really large chip, but eventually you will run out of power, but you get a lot of performance. And so there's always these, you can have 2 out of 3 kind of problem. And the question becomes, for any kind of problem you try to solve, what's the thing that you don't care about right now? And that's where you kind of like optimize away, and then you maximize the other ones. What changes with AI though is really we have this enormous amount of data, and we leave physics where we have closed form solutions that we can check. AI basically becomes so complex that we don't really know is it true or false. Whereas for physics, you can make an experiment, you can do a lower order model, you can check things. And so people feel more comfortable with when they know what to expect. AI, you basically feed the computer a lot of information, and then the computer does something. And that's why, even though at the very, very much underlying it's the same operations, it's the complexity of combining them that we cannot extrapolate as humans anymore what should be happening. And that's where then things get a little uncomfortable.
Now we have a little picture of what is being done to optimize hardware and AI systems. Where is the future of AI going? And how are engineers going to play a role in its future?
Engineers will make AI better and better. And AI is a fact of life, and it's not going to disappear. It's been around for a while, and from self-driving cars to anything, to your digital home assistant, to medical, it's going to be everywhere. And so engineers will spend a lot of effort in making it better. basically on the top level, the algorithms, getting back better data, but also getting better platforms so that the same problem can solved with a smaller device. So what right now your cell phone can do, eventually your watch will be doing, and then eventually maybe your contact lens will do. And whatever a big computer can do right now, eventually your laptop will do. So engineers will always push that forward because making it faster, it's going from dial-up internet to broadband changed everything. Having a computer doing AI to having your watch doing AI changes everything.
This podcast has been brought to you by Carnegie Mellon University's College of Engineering. I'm Alexandra George.